I'm going to speak for a few minutes on the topic of what you can do with NVDIMMs. And don't go there, by the way. This is all legit what you can do with NVDIMMs. I have to tell you, though, NVDIMMs almost seem like old hat right now, right? I mean, they've been around for several years now. They're well understood. They're standardized. And by the way, this is all wonderful, right? But yet, even so, people are still getting used to working with them, and as we've heard, applications using them and all that. So really still we're kind of at the tip of the iceberg for adoption, but the suppliers and such, and again, the software has been around for quite some time. So NVDIMMs are kind of the mainstream persistent memory, I think, and I've used them quite a bit myself and with my clients as well. And anytime you do this, so dial it back to 2015, if you will, we recognize that the SNIA, not only starting up, the efforts like the NVM programming and the entire twig that developed that model, but also we realized as an industry that this actually requires a big ecosystem. So we've heard from some of the OS vendors, right, on how, in particular, Stephen and Neil with Linux and Microsoft, about how the operating system folks have developed around this new technology, new back then, right, called NVDIMMs. And there's loads of support now in mainstream operating systems for all this, so that's great. And now we're seeing specific application adoption as well. So the ecosystem of the operating system vendors are there and hypervisors as well. And then, of course, there are numerous providers of NVDIMM technology, both -N and -P, which we'll talk about. And you can see them. Several of them are sponsors of this very conference, and I encourage you to go out and see their work out there. And then there is the standards side of the ecosystem, and JEDEC, and then us at the SNIA and UEFI. And again, there's lots of groups that have rallied around this technology and literally created very authoritative, very well-defined standards around several aspects of the technology, not just how does it fit in a 288-pin DIMM, right? But all that work is going on, and whether you realize it or not, it's fundamentally important, right? Standardization leads to mass adoption, and we have to take that step as an industry, I think, and we are. That's the good news, right? And then, of course, all the platform vendors and CPUs and processors of various flavors and all sorts of memory interconnect and the semiconductor vendors, and again the list goes on, but this all requires an ecosystem. Now you'll notice that the software piece is still kind of finding its way into the puzzle, but again I think we're only halfway through the double Olympic cycle, so we have 4 more years to go. But you can see, and just from the presentations today, how rapidly that's developing, which is a wonderful thing. Again, NVDIMMs are fundamentally the first type of, at least in this day and age, of persistent memory. So to review, and if you think this is old hat, that's fine. I'm glad you know this stuff already, but many of you don't. And there are basically 2 JEDEC-defined NVDIMM types called the -N and the -P. Don't ask, right? And the -N, again, and you can see that them running live out on the floor. Is effectively DRAM. That's what the operating system sees. It sees DRAM, and yet it contains a sufficient amount of NAND flash, basically half and half, right? The same amount of DRAM for the same amount of NAND, with controller technology in the middle, of course, and platform support, platform aka CPU. So when this is the whole idea here is that this is just like a DRAM RDIMM, except it has NAND flash to back up, that's the terminology used, to back itself up in the event of power loss, and of course requiring an external energy source. And where you can see the technology, since it is exposed as DRAM to the operating system, it is the same as DRAM. So don't let anybody tell you that NVDIMM-N is different than DRAM, because it's not. It contains DRAM. We know this. It smells like it, it acts like it, because it is. That's what's on the module. The module also, again, has a sufficient amount of NAND flash. And you can see, see this in operation. Now, again, these have been around for a while, right? And they're mature technology. They're very well mass-produced. There's several vendors that do this. And they are also extending the capacities of NVDIMM-N into the range that gets really interesting in terms of, scale-out types of persistent memory. So Then there's the NVDIMM-P world, which is yet emerging. And I say that because the standardization process is not yet done, but there's a lot of interest, especially in the last about 12 to 18 months, on -P. Again, several of the vendors, and Wendy's going to actually give you a very detailed look at a -P in that. And it's, you know, somewhat the same, but it's also fundamentally different because it's a device that has different amounts, different capacities of volatile memory and non-volatile memory. And the -P, again, there's a much more broad spectrum of what a -P can look like as opposed to a -N. So the ecosystem is yet developing around the -P. I'm very hopeful that it will. And in fact, we can start to see that already in 2019. So that's great. So what can you use it for? Well, let me tell you the story of one of my clients that actually has used NVDIMMs since 2015 as part of an operating system stack, a derivation of Linux as well. And they're using NVDIMMs not only for the sheer speed of it all, again, because they are DRAM, but also what do you do with the data inside an NVDIMM? In other words, how does it look? Right? Can I represent the data in mathematically speaking, different ways by encoding the data as it arrives in NVDIMMs to effectively make the NVDIMM area larger, right? As storage people, we know that there are several data reduction techniques that we've done on block storage over the years, right? This is well known. Well, take some of the same techniques and then modify them to use memory channels, and now you get some really interesting work where, you know, the first NVDIMMs were only 8 gigabytes in size. People consider that relatively small, right? Well, if I can mathematically represent the data in that to maybe only consume 2 gigabytes of that 8, I still have 6 gigabytes left over, therefore the NVDIMM is made more efficient. This is a really interesting approach. Right now, as NVDIMMs get bigger, that's great, but you know, you can imagine this applied to persistent memory in the future. That's one kind of very specific system-level use of an NVDIMM. And oh, by the way, the fact that it's persistent now gets us into the realm of what can you do with persistent memory, right? But you've seen some of this before. This is not new. But again, the whole idea here, and I like a lot of this, and especially at databases and storage, and those of you that know me know that I worked for a company as a CTO that developed scale-out file systems. File systems and NVDIMM-N, this is a wonderful combination. Why would you say that? Well, think about why file systems exist. Literally, why are they a thing? Right? They're a thing because we want to persist data, our files, number one, and we also want to persist information about said files. Right? We call that metadata. Right? Well, how do you store metadata? The whole storage of and handling of metadata is a whole other area in a file system. And as it turns out, if you've ever worked with file systems, metadata is key. Right? If you don't handle metadata correctly or efficiently, you know, the data is not going to be retrieved very well, and you lead to performance problems. There's all sorts of, you know, caveats. And I have to say this very carefully. If you've ever done FSCK on a petabyte and a half, you know what I'm talking about. Metadata is key. Right? So the use of NVDIMMs, persistent memory, to store metadata as opposed to A, volatile memory, right, which can go away at any moment, or B, very slow, you know, relatively speaking, block storage. This gets interesting. So I think there's a lot of work yet to be done right there. And literally, NVDIMMs are a wonderful solution. You know, fast like DRAM, you know, stores like storage. This is like Miller Lite, right? Tastes great, less filling. It's got both. It's a wonderful thing. So I like a lot of these areas. And again, you know, you address an NVDIMM exactly like you address DRAM. No difference, right? So this is NVDIMM-N. So, okay. Now I'm going to introduce Wendy. She's a distinguished engineer at ARM. Pay attention, people. She's at ARM. This is good, right? So we're going to bring her up. She's going to talk about persistent memory and NVDIMM-P.
All right. Yes, I am at ARM, and a couple other things I wanted to point out before we get started is at ARM I work in the memory and systems research group, and part of my tasks and part of my role is to actually work with a lot of the standards bodies, one of those being JEDEC. So this talk is basically trying to look at what NVDIMM-P looks like from a protocol perspective, and basically that's leveraging the work that I'm doing along with a lot of other colleagues within the JEDEC organization. So if we start just at a high level looking at the potential, this is in a lot of ways rehashing what a lot of the other speakers have looked at, but looking at the different potentials and where we see persistent memory, where it could be used in systems. And again, this is not an exhaustive list, but it is a couple of different options where we think persistent memory would be interesting. So like the -N solution, -P could be used for cases where persistence is something you want to take advantage of, where that non-volatility is something that you want to make use of. But one thing that NVDIMM-P brings to the table on top of that is the fact that you could have very large capacity. And potentially you could also have a solution that is a lower cost solution, given that the hope and the goal is that this new memory will be lower price per byte. So that combination of high capacity and low cost is something that we think is very interesting. And there's a lot of different technologies out there. This just lists a few of them. So again, not an exhaustive list of different technologies out there, but everything from technologies we have today, such as NAND, and down to DRAM and everything in between is something that could be considered and could be put on an NVDIMM-P bus. So there's a wide variety of technologies that we're targeting, and they all have varied characteristics. So if we look at how we're actually developing the NVDIMM-P protocol, similar to N, we are leveraging the DDR bus. So we're going to reuse the same electrical definitions for the command address and the data bus. Going to be able to plug into the same socket that a DRAM DIMM would be able to plug into. But we need to account for the fact that we want to interface to non-volatile media, and we want to interface to a multitude of types of non-volatile media. So we want this interface to be agnostic. So essentially, we are developing new opcodes that are media agnostic, going back to more memory semantic read-write type of opcodes, and then extending the opcode space, or the addressability space, so that we can actually address large capacity DIMMs. The spec right now actually supports up to 8 terabytes, so we are thinking definitely down the road of what could be possible. And the last thing I wanted to point out on this slide is we also needed to add a feedback channel. So a lot of these non-volatile medias, not all of them, but a good number of them have non-deterministic timing. So we needed a mechanism to be able to support that non-deterministic timing with with the protocol that we're developing. So this is a quick example of basically what that means looking at the read. So just a kind of a cartoon of a timing diagram. So essentially we have an extended read command that allows us to have larger capacity solutions. We have a single signal handshake. I'm not sure there's a typo there. That should just say response, not span. But we have a single signal response back, which tells the host controller when data is actually available. Then the host controller can issue another command to actually retrieve the data. And the data itself is always going to be done in a deterministic time. So what that means is that we can actually put multiple DIMMs on the same channel. We could actually mix DIMMs. We could have an NVDIMM and a DRAM DIMM both on the same channel because the data bus itself is still transferred in a deterministic way. I'm not going to go into a lot of details just because of time, but essentially there's additional metadata that we also incorporated into the protocol that's transmitted along with writes from the host, and from the DIMM it's transmitted back along with the read data. So a lot of that's used for RAS capability to verify transmission, as well as to enable the DIMM to do some interesting things like execute reads out of order or buffer write data, so that we incorporated some flow control aspects as well, so that write data could be buffered on the DIMM. So looking at the right side of things, there's been a lot of speakers who have talked about the fact that there's a use case for writes or for systems that don't require persistence. And for systems that do require persistence, there are varied levels of granularity or varied levels of persistent requirements that are possible. So keeping that in mind, there are two types of write commands that have been designed within the NVDIMM-P spec. One is an X-write command, which basically is just a normal write. That data could be indefinitely buffered on the DIMM in volatile media. There's nothing that explicitly tells the DIMM to push it to a persistent memory. There's also a P-write command, which is persistent write is what that stands for, and that's basically used to indicate to the DIMM that this is something we want to be persisted. And there are some additional flags that could be used to actually force that persist to happen and force a response back to the host controller so it knows when that media has actually made it to persistent memory. And along with the persistent write, there's another mechanism to actually flush data out to the persistent media, and that's a flush operation. So that could be done on a kind of a smaller granularity using write group IDs. There. Okay, sorry about that. So that could be done on a smaller granularity using a write group, or it could be done on a larger granularity where basically the system could say flush all outstanding persistent writes or just flush all outstanding writes. So that's analogous to what we have in the -N spec with the save N functionality for a power fail event. So I wanted to take a moment really to kind of correlate what we were doing in the NVDIMM-P specification in the protocol to some terms that, ooh, sorry about that. Okay, let me try again. Okay, I wanted to correlate what we've been doing to some terms that we typically use in industry. So first is just a point of persistency. And essentially what I mean by that term is it's a point where persistency is maintained. So that means that the data is either in persistent memory or it's in a place where energy backing is available. And then the other term is deep flush. And this is something that I leveraged from the SNIA NVM programming model, which according to the programming model, that's a push to the most reliable persistent domain available to software. Looking at the different types of DIMMs that are possible, we can have an energy-backed NVDIMM-P. NVDIMM-P does allow for buffering and potentially even caching, so any of that volatile media could be energy-backed by the DIMM or by the system, but there are cases that maybe we don't need that energy backing, so we could have a non-energy-backed DIMM as well. If we're talking about persistence and ensuring that persistence is maintained, when the DIMM is energy-backed, a point of persistence actually occurs as soon as you've reached an energy-backed source, so that could be on the host control or the host controller if that last level of FIFOs or queuing has energy backing, or at the very least it would be when the data crosses the DIMM boundary and has reached the energy-backed DIMM. But if we are talking about a deep flush, that's something where these extra commands that we've added and incorporated into NVDIMM-P, that's where we can actually leverage those and actually ensure that things were pushed actually to the persistent memory and we get a response back when that happens. So I wanted to just do a quick timing diagram here just to illustrate when you do need a persistent guarantee, what that looks like. So this illustrates basically a persistent write operation, write data sent from the host. When the DIMM actually has pushed the data to persistent memory, it will respond back to let the host know that is complete. If multiple outstanding persist operations are supported by the DIMM, the host can then query the status to understand what data actually has been persisted. Okay. So looking at what's next and where we want to go from here, just kind of highlighting it, we see, of course, emerging memory or emerging non-volatile memory is something that's going to redefine the memory subsystem. And right now, JEDEC and others are actually defining the solutions. So basically, this is a call to action for anyone who's interested. Please, come see me or come join JEDEC and share your insights. We have a lot of the core items balloted, but we are still finalizing the details and hammering out some aspects. And we are aligning right now. We're currently working on aligning the firmware to something very similar to the baby spec in NVDIMM-N. So thank you very much. And if you have any questions, come see me after.
For either myself or Wendy. Right here in the front, we'll get you a microphone.
So, are the Optane DC DIMMs following the JEDEC standards, or is that still in the works? Or-
Yeah, I think I will have to defer to my colleagues over
Oh
there
no,
for the
no,
answer to
sorry.
that
I
question.
meant, is Intel working with you to make sure everything is standardized?
Well, Intel is part of JEDEC, and Intel
Okay.
is a member of the task group, yes.
Cool.
Neither of us work for Intel, so
Right,
it's like,
exactly. So I can't speak beyond
can't
that.
speak for them. That's right.
Yes.
Here we go. You're good.
Group delay. Gil Russell, WebFeet Research. One of the things we've been looking at is the ability to execute in place or near data processing on the DIMM. And in fact, Intel's doing some of this on the NVDIMM for Crosspoint. It's a burst cache buffer with their DRAM. And that's a form of algorithm execution alignment for feeding hungry Xeon processors that haven't appeared yet. But the idea is, too bad too, the idea is pretty good where a lot of people are looking at algorithmic execution in place on the NVDIMMs. And it seems that the only thing we're seeing right now is an algorithm to expedite burst cache capabilities. I'm wondering if there's been any discussion at JEDEC regarding that capability.
There has been some discussion just regarding processing near memory capability. It's been at a very high level. So right now we've just been trying to hammer out the basic protocol and what we would need to do to talk to an NVDIMM-P. But that is something that I would see coming up in future discussions as we go towards next versions.
Yeah, there's some hyperdimensional stuff that's going on right now, and it's directed towards DNA, and it's heavily funded, by the way, right now.
Genomic sequencing. Yeah,
Yeah.
there's, as Wendy said, you know, there's some very high-level talks going on at the standards level. Now, one thing I will tell you is that we've had discussions in the SNIA. You know, we have a computational storage effort going on right now. Effectively, again, the whole concept trying to place processing elements on a device, you know, be it an SSD or what have you, but it certainly could end up being a persistent memory DIMM.
It needs to be
flavor.
coincident
It's the
to
same concept, and the SNIA is very interested in actually semiconductor vendors and module vendors that produce NVDIMMs to join effort with the current computational storage.
Yeah,
It's
I
interesting in
understand
a big
that,
hurry.
but what we're seeing here, Rob, is that we're talking about in-memory compute, and it has to be coincident to the in-memory compute for obvious reasons.
Oh, I get it. Remember, I used to work for Micron. Processor in memory is not an unfamiliar topic.
Yeah, are they going to give us any more room on the NVDIMM too?
I don't speak for Micron.
Well, you used to speak the language. You were complaining that they weren't enough
Oh,
aerial.
sure. No, I mean, you can go talk to the NVDIMM-N vendors. They're all working on 32 gig. This is good.
Yeah, that's enough.
Yeah.
Okay, thank you.
We have, let's see, do a time check. We got one more really quick question, if
Yeah,
any.
1 minute.
Right in, Marty, right in the front, right here.
So, Wendy, you share some of the timing details, things like that for the design protocol. Do you have particular media in the mind for tweaking those, timings and so forth? IHB talks about an MRAM, or IHB talks about a ReRAM, right? So maybe those characteristics and requirement for a protocol will be different, right, to some extent. So if you share what primary media you have in mind for designing those protocol.
So from a protocol perspective, the protocol itself is completely agnostic. And again, I think that it was Andy earlier who said that essentially what he made a comment about if your system can handle something, your application can handle something with longer latencies, I'm not going to inhibit that. So that's kind of the same general premise that we have right now in the NVDIMM-P. It's really going to be up to customer needs and applications and what's required from that standpoint.
And also, sorry, additional. When is the target to complete the standard JEDEC standard? Maybe align the timing to the DDR5?
So there's two different works going on right now. There's a DDR4 standard and a DDR5 standard. So the goal is to get the DDR4 standard done in the near term, so hopefully sometime this year. And yes, the DDR5 standard, we would like to align it with the DDR5 device standard as well, more than likely because we are having to reuse or leverage some of the work they've done and reference it. It would probably be at least a quarter delayed, but in that same ballpark.
All right, very good. Thank you, everybody. Appreciate that.